would like to thank the organizers for giving me the opportunity to talk about my work in this nice conference. I want to discuss some recent developments in the spinorial geometry of pseudo-Riemannian manifolds with an eye towards applications in supergravity and string theory. So, my goal is to introduce the elementary aspects of a new geometric framework, which I am developing in collaboration with Vicente Cortes in Hamburg and Kalin Lazaroyu in Korea. And this geometric framework, its main objective is to provide a convenient setup where to study general spinorial partial differential equations. In particular, the type of spinorial equations that appear in supergravity theories. In supergravity theory, there is the notion of supersymmetric theory, which is defined in terms of solutions to certain spinorial equations. These spinorial equations go beyond what is usually studied in the mathematical literature and therefore require new techniques for their study. In particular, in this context, it's very important to understand the moduli space of solutions to these spinor equations, which require new techniques that take into account that there are several geometric objects coupled and involved simultaneously in this type of equation. So this is the main goal of this research project, and its main properties are summarized here. So the framework that we are developing, this is ongoing work, it's very general in the sense that can be developed for real as well as complex spinors in every dimension and signature. Of course, we will mostly interested in Lorentzian and Riemannian signature, but other signatures are also possible. The notion of a spinor will be clarified in a moment. And the main idea, which lies at the core of this formalism, is that we are able to equivalently formulate spinors as polyforms, taking values in some appropriate bundle, which is defined in terms of the bundle of K4 algebras of the underlying pseudo-Riemannian manifold. And furthermore, every differential equation satisfied by the spinor epsilon, we map it to a differential equation for this polyform, which in a very relatively general setup will prove to be an equivalence. Therefore, in a sense, we transform the study of spinor satisfying partial differential equations into the study of polyform satisfying partial differential equations, which we consider, for reasons that we clarify in a moment, to be simple. In particular, because in order to define a spinor, I need to define a spinorial structure, but in order to define a polyform, I don't need to worry about that. And this is one of the simplifications that our formalism implements. This is especially convenient to study moduli spaces which involve metrics, because otherwise one has to keep track of how for example, a spin structure depends on the choice of metric. And again, because of this reason, it is especially well adapted to study evolution problems in Lorentzian geometry and the associated constraint equations on Cauchy surfaces, for example, in globally hyperbolic Lorentzian math. And I will give an example of an application in this context, given also that this is, of course, a conference on Lorentzian geometry. So let me clarify the basic setup on which I work. So we fix an oriented, well, as I said, the formalism can be developed for various signatures. And but I will be focusing on a Lorentzian manifold. Here, this definition is written for any signature, so never mind this, but we will assume this soon enough. So given a pseudo-Riemannian manifold of dimension D and signature P, Q, we denote by CLMG the bundle of P4 algebras. And with this information, we define the notion of a spinor as follows: as a section of a spinor bundle, where a spinor bundle of type gamma, where gamma is a representation of the Clifford algebra in that dimensional signature is a pair S comma gamma, where S is just a vector bundle, and gamma is a morphism of bundles of unidimensional and associative algebras, which, when restricted at every point over the underlying manifold, is isomorphic as a representation of a Clifford algebra to our given gamma. Okay, so by definition, sections of this type of vector bundle will be called spinors, and if we want to stress the type, they will be spinors of type gamma. So in the following, now this is one of the restrictions that we're going to make, we assume that the signature satisfies P, the number of classes, minus Q, the number of minuses, is equal 0,2 mod 8, which means that we are in the so-called real simple case, in the sense that the Clifford algebra in this dimensional signature is a simple real Clifford algebra, which is actually isomorphic to a matrix real algebra. Furthermore, we assume gamma to be irreducible. So this is the setup in which we work. And this is the setup in which we obtain our results, and it is ongoing work to extend this geometric framework that I'm going to introduce for other signatures and dimensions. So one quick remark here, existence of such S comma gamma, such a spinor bundle, is in general obstructed, and luckily enough for the signature that we are choosing, the obstruction is very familiar. So in this case, it was proven in this reference by Lorentzian myself that S comma gamma exists if and only if G admits a spin structure. This is not the case, by the way, in other dimensions of signatures. You can find a full list of possibilities here, and in general, the type of spinorial structure that one obtains is more general than a spin structure, and is the so-called Lipschitz structure, as introduced by Friedrich and Trautmann. So they introduced this notion, which we re-encounter years later in this work. Okay, so since the most general situation that we can have for this definition of a spinor bundle, which, as you can see, doesn't assume any spinorial structure a priori, but by these results, since the most general situation that we can have is a spin structure, then with a loss of generality, we can assume that our spinor bundle is actually associated to a spin structure, and in particular, the Levi-Civita connection on our pseudo-Riemannian manifold, which we can think as being a Lorentzian manifold. Let's keep it a Lorentzian manifold from now on. So the Levi-Civita connection on our Lorentzian manifold leads to the spinor bundle, and which we denote with the same symbol, they lead to the spinor bundle, and given any one form taking values in the endomorphisms of S and any endomorphism of S, we want to study this differential equation. So why do we want to study this differential equation? Well, it's essentially the most natural, general, first-order differential connection involving the Levi-Civita connection acting on the spin. And more importantly, this equation here occurs as one of the killing spinor equations of every supergravity theory is of this type. Perhaps for a different type of spinor, but the killing spinor equations of every supergravity theory contain an equation which is of this type, plus an equation which is of this type, namely epsilon belongs to the kernel of a given endomorphism. This endomorphism can be, for example, the curvature of a connection on a principal bundle, which is acting through Clifford multiplication on the spinor. So this, I just wanted to mention here that this possibility is also considered in our work, but in the following, I will take this to be vanishing, E equals 0, and I will focus on this equation. Okay, well, there is a very obvious particular case, which is of much interest and relevance, which is taking this one form taking values in endomorphisms of S as being 0. In this case, we recover the study of parallel spinors, which have been studied by several authors. Baum, Leisner, Lichewski, Müller, which, if I'm not mistaken, just gave a talk here. That's a funny coincidence. And even in this very classical setup, which has already studied in the literature, our formalism also provides new results which can be proven very efficiently. So, okay, let's continue. So in order to propose the basic result of our framework, we need to choose another piece of data, which is an admissible pairing on our spinor bundle. This is an inner product, which has nice properties with respect to Clifford multiplication. It is equivalent in a very particular sense of in a very particular meaning. It is non-degenerate, and it is either symmetric or skew. This depends on dimension and signature, but either you can choose it as only a skew, only symmetric, or perhaps you can choose it either symmetric or skew. This is all the possibilities are tabulated. And furthermore, if it is not positive definite, which in general won't be, then it is of a split signet. Okay, so using this admissible pairing, we can, which we fix, we can introduce a quadratic map which takes a spinor and it maps it to an endomorphism of the spinor bundle by taking the dual of the spinor with respect to the given admissible pairing. And once we are introduce this quadratic map, we are almost completely set to introduce the main idea in this framework, which is this commutative triangle, where this is the bundle of T4 algebras. This is the endomorphism bundle. This is our representation, which in this case is an isomorphism of bundles of algebras, unital associative algebras. And here we introduce the bundle of forms, the exterior algebra bundle, equipped with a quantization of the wedge product, which makes the canonical identification between the bundle of Clifford algebras and the bundle of polyforms into an isomorphism of bundles of unital and associative algebras. This is the so-called geometric algebra. I think that's one of its standard names. And if we take a one form and we make it act on a polyform, it acts in this familiar way, I'm sure for most of us. So, given this commutative triangle, we have that our quadratic map goes from S into the endomorphisms, and therefore, using this way, this path, we can associate to every spinor here a polyform here, which is equipped with this diamond product, this geometric product. And this is the spinor quadratic map, which is at the core of this formalism, because as I was saying, we're going to transform spinors into polyforms, and this is the way we do it. Okay, so the fact that you can associate spinors, polyforms to spinors was well known in the literature. This was mentioned, for example, and discussed in the seminal book by Michelson and Lawson, Spin Geometry. And, for example, through this map, one can associate to a spinor in 6 Euclidean dimensions its Calabi-Yau structure, or to a spinor in 8 dimensions its spin 7 structure, which is a certain type of admissible 4 form. Everything works out naturally from this spinor quadratic map. The open problem, important problem for us, is that clearly the image is far from being the full space of polyforms. So the important problem is to characterize the image of this map in algebraic and convenient terms. Because if we do that, if we can obtain a set of algebraic equations which guarantees that a polyform is in the image of this map, then we can forget about, in a sense, the map and the spinor, because we know that this polyform will be in the image of this map, or at least a spin. This is what this theorem clarifies now. I didn't put the archive number, sorry about that. This is from 2010, so it's relatively recent. So here in this theorem, we are already, by the way, if I'm going over time, please let me know. Anyway, in this theorem, we already use this quadratic map to transport in an equivalent way the information contained in a spinor and the equation itself. And the result is the following. So given a spinor satisfying this equation, so we have a spinor satisfying this equation if and only if there exists a nowhere vanishing polyform that satisfies these equations here, which are algebraic, and this differential equation here. Let me clarify a bit. For a fixed polyform such that this is zero. This is essentially S of alpha is a trace in the Kähler-Attiyah bundle. This is called the Kähler-Attiyah bundle. So, but it essentially takes the zero order component of the polyform. So there is no mystery here. The zero order component of the polyform. These are the canonical automorphisms and anti-automorphisms of the bundle of Clifford algebras, which essentially interchange order of the elements of a canonical orthonormal, sorry, of an orthonormal basis locally. And this is a given sign, which depends on dimensional signature. And, well, this is the geometric product diamond. So this guarantees that alpha will be the image of a spinor through this map. And then this equation is satisfied if and only if this equation is satisfied, where this A hat is the transport of the endomorphism part of A to a polyform itself, and therefore acts through the diamond product. So therefore, since this is an if and only if, now we can forget about the spinors. Yes, we can forget about the spinor bundles. We can just study a spinorial geometry problem purely from this geometric framework of polyform. Particularly, we can study the moduli space of this equation, which, at least in the situation we're interested in, will be easier than if we had to keep track of the spinor bundles and spinorial structures that we began with. So it is better to see this in play, I believe. Let me just give you some corollaries in 4 dimensions of this theorem. So a spacetime so we want to apply to 4 Lorentzian dimensions, which falls into the cases we are considering, p minus 2 equals 0, 2 modulo 8. So a spacetime for manifold M admits a nowhere vanishing spinor if and only if there exists a parabolic pair, which consists of a one form. Forget about the equivalence class. I don't have time to explain this properly here, but so we can think of this as a pair of one forms where U is null and L is space-like and satisfies this condition. It is orthogonal to U and it has norm 1. So a spacetime for manifold admits a nowhere vanishing spinor if and only if admits a pair of one forms that satisfy these conditions. And if you give me this pair of one forms, I can recover the spinor modulo a global sign. So this gives a convenient description of spinors in 4 dimensions, which can be used to now obtain the following geometric result. A spacetime for manifold admits a non-trivial real Killing spinor of Killing constant lambda over 2. These real Killing spinors are defined as nabla G applied to epsilon equal to lambda halves times epsilon with respect to Clifford multiplication of some vector field. It's the standard notion of real Killing spinor, but in Lorentzian symmetry. So now we obtain the following, I believe, convenient result. Real Killing spinors are equivalent to pair of one form satisfying this equation here. No spinors around, no spinor bundles. Simply this equation for some one form cap. And in particular, of course, if lambda equals 0, then we obtain a characterization of parallel spinors in terms of the parallelicity of U, which was well known, the existence of a null one form in this case, and this extra equation for a space-like one form of norm 1 in terms of certain one form K. So, by the way, this problem has not been studied that much in the literature. It has been studied by Philipp Leitner, but there are many open problems related to this particular problem. So just to finish up, We have used this formulation to study the evolution problem and constraint equations of a parallel spinor in 4 Lorentzian dimensions, and we have obtained, just to flash real quick this result, we have obtained a new geometric characterization of the flow evolution equations of a parallel spinor on a Lorentzian globally hyperbolic for manifold, which I am explaining here in the particular case of having a globally hyperbolic for manifold of Comovin type, we call it, which is nothing but a globally hyperbolic for manifold for which the time factor, TT time of the metric, is 1. So in this case, we have the result in more generality, but just to give you a feeling of the type of geometric results that we can get. Using the previous formulation, we are able to rewrite the flow equations, which we call the Comovin parallel spinor flow, the evolution equation, as the evolution equations or flow equations for a family of sections of the frame bundle of an oriented free manifold, which are required to satisfy this differential system here, where theta t is the second fundamental form of the embedding of the Cauchy surface. And using this convenient formulation, we were able, in our paper with Mr. Angel Murcia, to obtain new flows of parallel spinors explicitly to characterize the differentiable topology of the Cauchy surface. For example, we characterize all compact Cauchy surfaces that can appear in this context, and we obtain other various results. This is also a very recent paper by Murcia and myself, recently posted on ARC. So, well, this was everything. I hope I didn't go over time too much. And I hope I gave you a feeling of what this geometric framework aims to do and the type of problems it can address. So thanks a lot. That's it.